All right, everyone. So I said I would work through the practice problems 6 through 10. On my sheet, I have them written out on the back, so I'm going to just work through them with you so you can see how to work the problem, but I want you to see it. Okay. Number 6. In an amusement park, there is a free fall ride that drops riders straight down for 30.0 meters. What velocity is the ride traveling at when it reaches the bottom of this straight drop? Okay. Okay, so what do I know from this problem? I know that V naught is 0, right? So I write that out. Okay, I also know my displacement is 30.0 meters. So I write that down as well. And I also know my acceleration, right? This is a free fall problem. You know your acceleration. Okay, and then I'm going to give my direction at the end. Okay, so the equation that we're going to use is v squared equal v naught plus 2 times my acceleration times my displacement. And that should look familiar to you guys. Remember, we went over that in class on how you get it. So then v squared 0, right? We already defined, I already told you that v naught 0 plus 2 9.8 meters per second squared. Now I also could have this as a negative number if I define, we talked about that in class, and I'm going to just do mine at the end. All right, so that's going to give me meters squared per second squared, but then when I take the square root, I'm going to get meters per second, and then when I calculate this out, I get 24 meters per second, and I'm going to say down. So please don't forget to define downward, okay? And hopefully that makes sense. Problem 7. A physics student drops a rock off a cliff. If the rock takes 3.5 seconds to reach the bottom of the cliff, how tall is the cliff in meters? We worked one similar to this in class. Okay, so showing you just defining direction right off the bat, I'm going to say downward is my positive direction. Okay, and the equation I'm going to use for this problem is delta x equals v naught time plus 1/2 acceleration time squared. Okay, and my problem is asking me for how tall is the cliff. Okay, so that is what we're looking for. All right, my v naught is 0, right? It tells me my time is 3.5 seconds. And my acceleration, you guys know in free fall problems, 9.8 meters per second squared. So this is basically just a plug and chug problem. 0 times 3.5 seconds. That will cancel out though. 1/2 times 9.8 meters per second squared times 3.5 seconds. I will square that, so my second squared will end up canceling out when I do my math. And then when I calculate that out, I get 6.0 times 10 to the first meters. I want 2 significant digits, so that's the way I have to write it. Okay, let's look at problem 8. A parachute falls from a plane for 5.0 seconds before opening, a parachutist follows from a plane for 5.0 seconds before opening the parachute. How fast is he traveling when he opens his parachute? Okay, so I'm going to define downward direction as positive again. So however you need to make that notation for you. Okay, my parachutist is dropping out of a plane, but my V naught is going to be 0. He's not moving at the point from which, okay? And then I'm going to use my equation, V equal V naught plus AT, acceleration times time. Okay, and it gives me my time. Let's look at the problem really quick. 5.0 seconds. And I'm looking for my velocity. I know my acceleration, and because I define my downward direction as positive, it's going to be positive, so 9.8 meters per second squared. And then I plug and chug to get my answer. So V equals 0 plus acceleration, 9.8 meters per second squared, times 5.0 seconds. Just going to take away one of these. And then when I calculate that out, I get 49 meters per second, and it's a positive number, and I defined it as going downward, so downward. Okay, so 49 meters per second. I need to have 2 significant figures. Hopefully that makes sense to you guys. 2 more problems, let's go. Number 9, a child throws a ball up in the air with an initial velocity of 3.9 meters per second. What is the maximum height that the ball reaches? We talked about these type of problems in class. So number 9, I'm going to define my upward motion as positive. So my downward's going to be negative. I'm going to use my equation, it's going to equal V naught squared plus 2 times the acceleration times my displacement. Okay. And then based on the problem, I know that he throws it up in the air with initial velocity of 3.9 meters per second. What's the maximum height that the ball reaches? Okay, so all right, so I'm looking for my maximum height. So I'm looking for delta x. And when I rearrange this equation over here, times my acceleration. I'm looking for the maximum height the ball reaches. So my final velocity is going to be 0. At that point, when it reaches when it stops at that top, that instantaneous, that final velocity is going to be 0. I know my V naught tells me 3.9 meters per second. I know what my acceleration is going to be, right? I defined my upward motion as positive, so my acceleration is going to need to be negative. Okay, so then when I plug my numbers in, I'm going to get 0 squared minus 3.9 meters per second. And I have to square that over 2 times negative 9.8 meters per second squared. Okay, so when I square this, I'm going to get meters squared per second squared. Down here I have meters per second squared, so I'm going to get meters. I'm also going to get a positive number because I'm going to square this and it'll be negative. And then 2 times negative 9.8 is a negative number, so it's going to give me a positive number. And I get 0.78 meters, which lines up. I need 2 significant figures. All right, hopefully that makes sense to you. We just have one more practice problem to work through. Last one of the practice problems. Number 10. A physics student stands on a ladder 12 feet above the ground and throws a ball up into the air. If it takes the ball 4.2 seconds to hit the ground, what is the ball's initial velocity? Okay. So in this problem, I'm going to define upward motion as positive. Again, you could do the reverse as long as you're consistent. Whatever way you want to denote it. I know my displacement is negative 12 feet. It's up on the ladder. I know my time is 4.2 seconds. I know my acceleration and free fall problem. I'm going to go ahead and use the one that I know that already matches up with my units. So I'm going to do 32 feet per second squared, right? And then I'm looking for the initial velocity. All right, so the equation I'm going to use, we know displacement, so I'm going to use delta x equal v naught t plus 1/2 acceleration times time squared. Okay, and if I plug it in, get negative 12 feet equals v naught times 4.2 seconds plus 1/2. Because I defined upward motion as positive, my acceleration needs to be negative. I should have a negative here. Sorry about that, you guys. Negative 32 feet per second squared times 4.2 seconds, and then square that. All right, and then when I rearrange, I get negative 12 feet plus 16 feet per second squared. And then that's going to be times 4.2 seconds squared. So that's right. On the bottom, I'm going to get 4.2 seconds. And that's going to leave me with 64 feet per seconds. And then I'm going to say upward. I know this because I defined my upward motion as positive, and it's positive, but still, let's just put it there and be super clear. Okay, let's move on to the review questions from here. All right, I've already worked these out, and I just want to go over what the answers are. So for review question for Module 2, number 1, what are 2 conditions that must be met before you can use the 3 equations we derived in this module? That was our lecture 1 on this module. Well, it needs to have straight line motion. We talked about that. And there needs to be constant acceleration of the object, okay? Number 2, what is air resistance? How does air resistance affect the acceleration for falling objects? Okay, well, you guys know right away that the air resistant affects it by slowing it down, right? By reducing it. And it's kind of a little bit of a mouthful, kind of put what your book said here, but air resistance, you sometimes hear it referred to as drag. It happens because an object that falls must shove all the air and air atoms and molecules under it out of the way so it can fall, right? It happens very quickly, but that's what has to happen. So those atoms and molecules resist the shoving, which reduces its acceleration. Okay? Number 3, what is the definition of free fall? It's motion of an object when it falls solely under the influence of gravity. So we neglect air resistance when we're in this module when we're talking about free fall. Number 4, a very picky physicist says that no object can really experience free fall when falling near the surface of the earth. Explain why the physicist is technically correct. Well, since all objects falling near the surface of the earth are technically in air, they do experience air resistance. So it wouldn't solely be under the influence of gravity. But we talked about in lecture about how it's almost negligible. So that's why in these problems, we're not considering it. Okay, number 5. Even though the physicist in question 4 is technically correct, explain why we still assume most objects falling near the surface of the earth are indeed in free fall. And again, I just said, but they aren't strongly affected by the air resistance. It's almost negligible in these problems, and so that's why. Number 6. If an object is thrown up in the air, where is its velocity 0? When its velocity is 0, what is its acceleration? We touched on this in class. So where its velocity is 0 is at that maximum height, right? The maximum height that the ball or whatever the object reaches. When its velocity is 0, what is the acceleration? The acceleration is same as in free fall problems, 9.8 meters per second squared downward, or 32 feet per second squared downward, okay? Depending on how you define. Number 7, on the moon, gravity is significantly weaker. Sorry, you guys, I'm having trouble reading today. Weaker than on Earth. Would you expect the acceleration due to gravity on the moon to be larger, smaller, or the same as compared to the acceleration due to gravity on Earth? Well, it would be smaller. If gravity is weaker, it can't accelerate things as strongly, right? So therefore, the acceleration due to gravity on the moon is going to be smaller than that of Earth. Number 8, a feather and a penny are put in a long glass tube, and all of the air is sucked out of the tube. While inside the tube, will the feather fall faster, slower than, or the same as the penny? Well, think about it. All the air has been sucked out. If there's no air, there's no air resistance. So both would only be affected by gravity, so they would fall at exactly the same rate. Number 9. A ball is thrown up in the air with an initial velocity of 1.2 meters per second. If the ball is caught at exactly the same height from which it was thrown, what will its velocity be? So this is where the ball takes off and goes up and comes back down, and they're talking about it hitting the exact point from which it was thrown at. It would have the same velocity, just in the opposite direction. So it would be negative 1.2 meters per second, or you could say 1.2 meters per second down, okay? And lastly, number 10, suppose you have 2 balls of equal mass. Although their masses are equal, they are made of different substances. As a result, the first ball is significantly smaller than the second ball. Which ball has the highest terminal velocity? Well, the first ball will have the higher terminal velocity. It's significantly smaller. So air resistance depends on mass, shape, and surface area of objects. So if the mass is equal and the shapes are both balls, the smaller ball has a smaller surface area, so it's going to experience less air resistance. So gravity can accelerate it more quickly. All right, that is it for the review questions, and now I'll give you a couple of hints on your test. Okay, so make sure that for your test, you understand air resistance and terminal velocity, and understand them so that you can explain them to me, and understand them so that in problems, if they say, if the condition is this, how would it affect this? Okay? Know how to work problems for all of the equations that we derived at the beginning of this module. Okay? So you need to know v squared equals v naught squared plus 2 times the acceleration times the displacement. Displacement equals v naught times time plus 1/2 times the acceleration times time squared, right? All three of the equations that we worked with. Don't forget what your acceleration is going to be on free fall problems. You guys should just know that. Otherwise, if you're comfortable with the things we just went over and the practice problems and the review questions, I think you're going to do great. So good luck. Make sure you show me all of your work, please. For full credit, show me all of your work. Don't forget to include units, and your units should make sense with what you're trying to get. If you're trying to get displacement, you know it should be in meters, feet, something like that. If you end up with meters per second, something went wrong, and it can alert you to go back and look and see what you did, okay? Also, don't forget significant figures. Pay attention whether you're adding, subtracting. If you're adding and subtracting, significant figures goes with the number of the least, it goes to the least precise. If you're multiplying and dividing, then you use significant figures of the number that has the least significant figures, okay? So remember your rules there. And I will see you guys on Monday.